If A and B are vertices of a polyhedron, define the distance d of AB to be the minimum number of edges of the polyhedron one must traverse in order to connect A and B. For example, if AB is an edge of the polyhedron, then the distance between A and B is 1, but if AC and CB are edges and AB is not an edge, then the distance between A and B is 2. Let Q, R, and S be randomly chosen distinct vertices of a regular icosahedron, which is a regular polyhedron made up of 20 equilateral triangles. What is the probability that the distance between Q and R is greater than the distance between R and S? So for this problem, it is definitely going to be worth knowing what an icosahedron looks like and how to draw it. So in order to draw this icosahedron, we're going to first draw one vertex of this icosahedron. And now noting that in icosahedron, every vertex is going to be adjacent to 5 other vertices arranged in a regular pentagon. So once we draw one vertex, it's going to be adjacent to 5 other vertices that are arranged in a pentagon. And these are also the vertices that are distance 1 away from the top vertex that we drew first. Now the vertices that are distance 2 away, they're also going to form a regular pentagon, but slightly rotated. So something like this. Lastly, there is one vertex that is distance 3 from the top vertex. And we'll just connect the pairs of vertices like so. And so this is roughly what an icosahedron looks like. So the main reason why we drew it this way is so that we can now determine all the distances from one particular vertex. And so specifically, we're going to fix this top vertex as R. And the reason why we're doing this is because we're comparing the distance between R and Q and R and S. So if we fix one of the vertices as R, then we can essentially reduce the problem to saying, what's the probability that Q is further than S? And because we drew it this way, we know that the 5 vertices that are adjacent to R, so these 5 red vertices are going to be distance 1 from R. Now, next, these 5 vertices that I'm coloring orange, these are the vertices that are distance 2 from R. Lastly, the vertex that is opposite from R, this is distance 3 from R. So out of the remaining 11 vertices, we're going to choose 2 of them to represent Q and S, and we're looking for the probability that Q is further from R than S is. So there are a few ways to solve the problem at this point. One way we can solve this is we can choose the location of Q, and that will determine where S will be. So as an example, so we need to find the probability that the distance between Q and R is greater than the distance between R and S. So we can divide this problem into a couple cases. First, we know that if Q is distance 1 away from R, right? So if Q was, say, this point right here, then there's no way that S can be closer to R than Q is. Because Q, R, and S are different vertices, the only possibility would be that R is equal to S. So Q cannot be one of the red vertices. Now, if Q is one of the 5 orange vertices, then S can be any of the 5 red vertices. So we see that there are 11 times 10 ways, or 110 ways to choose 2 vertices Q and S out of the remaining 11. And we see that if Q is any of the 5 orange vertices, then S can be any of the 5 red vertices. So how many ways can we choose an orange vertex for Q and a red vertex for S? This is simply 5 times 5. Lastly, Q can also be the blue vertex that is distance 3 from R. So Q can be this vertex right here, in which any vertex can be chosen as S, since any vertex will be closer to R than Q. So if Q is this blue vertex at the bottom, then there are 10 ways to choose S. And now we can just compute the probability as 35 over 110, and this simplifies to 7 over 22. So the answer is A.